Every Gen Chem 2 class has a kinetics rate law experiment. They're pretty fun to do, and they tend to involve color changes, which makes it interesting. They're also very visual. What you're seeing is the format of how the data you get from a kinetics rate law experiment looks. We're going to do 2 of them today to show you how to work them and how to solve for a rate law. And I'm also going to show you how to read them. So you, in homework questions, would be giving something in a table format like this. You wouldn't have to have actually performed it for homework, obviously, but you'll still have this kind of a format. The rate does not have to be on the left. It could be on the right, so pay attention to where those values are. So what you do in these experiments is you'll just do a first experiment. You'll figure out this molarity of a reactant, and then you'll run a reaction, and you'll just use a stopwatch and time it. And the cool thing is they're usually like, I don't know, let's say it's purple, the A, when you have A in there. But when A has been converted to all product, the product is maybe colorless. So you can see the purple getting lighter and lighter, and then all of a sudden you don't have any color at all. So you just time how long it takes for like the color to go away. And then you calculate the rate. The rate is how much molarity is lost per second. So it would be 0.3 divided by whatever the time that took. And that would be your first experiment. And then you jump and you reset the whole thing up. But this time you do it with a different molarity. And you calculate that rate law and then a final molarity. So that's what these columns are meaning. It's just a way to kind of tabulate rate versus concentration all in one little format. Now I do have a few tips with these. One tip is to set the rate law so they're all on the same magnitude. This makes us not obey scientific notation. So on your final report, you wouldn't do this, but to help you get to the rate law, it saves time later on. It just helps you visually see this. So notice that this is 10 to the third, 10 to the third, but then this is 10 to the 2. We could set this one to be 10 to the third also. So if I just move that decimal place over, that will make this 10 to the third, and my decimal ends up being over here. Again, not scientific notation, but now we can really see, oh, this is a smaller number than this. That's a pretty big number comparatively. So we can really see what's going on with these rate laws. Also, because it's experimental data, they won't come out like perfectly even whole numbers, but they'll come close, and so you'll just go with the whole number that you get. Here's the format of your rate law. So rate is equal to K times A to the M. So to figure out the rate law, what you need is at least 2 experiments, and you'll set one experiment over the other experiment, and you set it up like this. So we'll take this rate law right here. They're going to be over each other. And I always like the larger rate to be on top. So like the 26 might be on top. So that would be rate 2. And I'm going to do it over, I'll just pick rate 1. And then this is 2 over 1. Now there's a way to simplify this, and then this will help you have a format for every single one of these if you like to do it mathematically. I'll also show you how to do it, we call it by inspection. And for some people, this is very natural, and for some people, it doesn't work as well, and they just prefer having the formula. So because the reactions are going to be performed right after each other in the same lab, the temperature is going to be the same, the pressure is going to be the same. And since it's the same reaction, they have the same K value. So what that means is that our K's cancel. So that's the first thing. I can rewrite it with the K totally being gone from there. The second thing is that exponent rules let me combine A2 and A1 in one parentheses, like this. I'm still going to keep those over each other. So before, it looked like that. And what I did, and I'll just copy this down a level, was I just put them both in the same parentheses. And I just split up my lines so that it kind of looked a little bit neater. Now this is the format that a one reactant rate law, like if you want to have everything all out of it and not have the K's in it, that's the format that you're going to use. So then I just fill in the information. So rate 2, and I'm going to keep it as at 26 times 10 to the minus 3 over rate 1, which is 8.6 times 10 to the minus 3 equals, and then A2 is 0.9 over A1, which is 0.3 raised to the M. I'm going to bring my calculator over. It did not let me bring it over. There we go. And so I'm going to do, notice that it's the times 10 to this, since they're all on the same scale, I can also not have to worry about them in my calculator. I can just say they're canceled out. So I just have 26 divided by 8.6, and that gives me 3. And again, like I said, it's not going to come out perfect because this is experimental data. So, but I'm going to round that to 3. If it was like 3.5, you wouldn't round it, but the 3 you can. And then this is 3 to the n. Now, there are some rules that you can do where you can take the log of both sides, and when you do that, the n goes in front, and you can do n equals log of 3 over log of 3, which is 1. Or you can just say that you could see that this was 3 and that this was 3 to the m. And if that one has an understood exponent of 1, which it does, 3 is 3, whether it's 3 raised to the 1 or just 3, then you can say that that's what the exponent is. So either way you prefer to work the problem, that's how you do it. Now, how could you write the final version? It's just rate equals K, A. And we usually don't put anything here. It's an understood one, but just so that you can see that I'm putting a 1 there. Can you do this by inspection and bypass all the math? If you're good at it, yeah, you can. So if we look right here, you pick a set of changes that you can see fairly well visually. It might actually be easier to do this set of changes because that's a factor of 9. And then you can see, if you aren't completely sure with your calculator, you can, like if you just want to see what the change is on the other side, 26 divided by 2.8 gives me like 9.3. Again, that's not the best. I would have rather have just been 9, but it's about 9, 10 to the 9. And so you can see that if they're changing the same, the exponent of a must be 1. So that's how you visually look at it. It doesn't matter which set of experiments. So I can do that again with a different set of experiments. So as I go here to here, that's times 3. And as I go from here to here, remember that's 8.6 to 26. So that's times 3. If you're not sure, again, you can check with the calculator. 26 divided by 8.6 gives me, 3. So that one actually worked out really nice, that experiment. And again, it's still that same change though. It's times 3 to the 1 is equal to 3. So you can do them visually or you can do them with the math.